Now let's review drawing free body diagrams and friction. Remember, when you draw a free body diagram, always read the problem. Always identify all of your forces. Draw your object as a box. Draw your forces as vectors. Have all of your forces start on the object. Remember, the length of the arrow is the magnitude of the vector, so a longer arrow means a larger force, and the arrow should always point in that direction of that force. This is an example of a good free body diagram where all the forces start on the object and go away. And this is an example of a bad one where the forces are pointing toward the box. Remember, friction is a contact force that opposes motion, not necessarily acceleration. It depends upon the normal force, and that there are two kinds, static and kinetic. Static friction means there's no motion, and it's less than or equal to μs, the coefficient of static friction, times the normal force. We're usually referring to the maximum value of static friction, and that's equal to μs Fn. To convince yourself that static friction changes, if you stand up and push gently on the table before it moves, you're applying one force. Well, friction is applying the same force on the table to keep it from moving. If you apply a larger force, there will be even more friction until you reach that magic point where it just starts to move. And then it jumps up here to kinetic friction. And then the kinetic friction is always equal to mu k times the normal force. And remember, static friction is always greater than kinetic friction. Now imagine you're moving a trunk. Alright, if you were to graph the frictional force being applied by you, you would see it increases linearly until it hits this magic point right here. This is the magic point, the maximum static friction. If you were to keep applying force, you would find that you would go into a kinetic situation where as the force increases, it instantly drops down and you have a constant kinetic friction from there on. So once you get that trunk moving, you can apply less force to get it moving at a constant speed. Now, what else do you need to know? Friction in tires. Everyone knows when you drive your car that friction keeps you on the road. And if you don't believe it, try driving on ice. What kind of friction occurs on a rolling tire between it and the ground? It turns out it is static, because at the point of contact, instantaneously the tire has no velocity. Right where the rubber meets the road, right there, the tire is instantly not moving. Now, we could do a wonderful derivation here, but we're not going to. It turns out the center of the hub is moving at the speed of your car, but the top of the hub is moving twice the speed of your car. But what if you start skidding? What if your brakes lock up and you start skidding or you get on ice? It's no longer rolling but sliding, okay? And once it's sliding, it's just exactly like a box on the floor. It's kinetic. Now, there's helping friction, there's hindering friction. Helping friction is friction we need in everyday life. If you're walking on ice and you don't have any friction, you will find very quickly that you needed friction. So there's always friction when you're walking or driving or sitting. Let's discuss something really quick. You're walking and you're going to apologize. This is my foot. There's my foot. There's my ankle. Nice ankle. And I'm walking this direction. So my velocity is this direction. What's the direction of friction? Now, you're going to want to say it's to the right, but let's think about this. When I walk, I put my foot down, and my heel kind of goes up like this, and I'm pushing my foot backwards. So my foot is sliding backwards on the ground. And if you don't believe it, watch me on ice sometime. So if my foot is moving backwards, motion is to the left, friction opposes motion. So friction is forward. Think about it. Friction actually pushes you forward. Hindering friction? Well, if you don't have enough oil to cool your engine and to reduce friction, you wind up overheating. Rug burns. Sliding down slides when it's warm on bare legs. You definitely can get some friction going there. Now let's work a problem. Suppose we have an applied force. So that's my applied force right there. Okay. And go on and label it up in here if you need to. Just put a big F over it. It's used to accelerate a 100 Newton object. Now when I tell you something's 100 newtons, I'm telling you its weight. This is Fg. Okay, it's accelerating to the right across a frictional surface, so I know I'm going to have friction. The object encounters 10 newtons of friction. Cool, I told myself what it was. There's my friction. Determine the normal force, net force, mass, and acceleration. Once again, there's a lot we can find in these problems. All right, what am I given? I'm given the applied force is 50. The force due to gravity is 100, and the frictional force is 10. Now remember, the first thing you want to do is, if I give you mass, find weight. If I give you weight, find mass. So, let's find the mass here. Fg equals mg. So the mass is Fg divided by g. So I left off my equal signs. So Fg is 100 divided by 9.8, or it's equal to 10.2 kilograms. Now we need to apply Newton's law in x and y. This is accelerating to the right. Okay. In the y direction, it's not accelerating at all. So in the y direction, F net is 0. The only forces I have acting in y are Fn, positive, minus Fg, negative, and that has to equal 0. So the normal force equals Fg, I already have Fg, is 100 newtons. Next, we apply Newton in the x direction. Now F net in the x direction is ma. It's this mass times acceleration. Now, we're going to need our mass in just a minute. The first thing, since I have the forces, I can find the net force. It's just F applied minus friction, so it's 50 minus 10, or 40 newtons. So I can find the net force by adding the forces from my free body diagram. To find acceleration, I go to Newton's law, F net equals ma. Solve for a, which is F net divided by m. My net force, which I got from my previous problem, is 40 newtons. Divided by my mass, which I got up here. And I get that the acceleration is 3.92 meters per second squared. All right, what is the coefficient of friction? Well, first of all, let's rewrite all of our givens. We're on a new page. And I know friction is mu Fn. So let me solve for this mu, this funky Greek letter. So mu is the force of friction divided by the normal force. Friction is 10 newtons from the givens. The normal force is 100 newtons. We figured that out on the previous page. So we have mu is 0.1. Did I forget the units? No, there are no units. Now, one of the best ways to experience friction is with the skateboard lab. So everybody is going to have a chance to weigh themselves when we break into the lab. Now, when you step on the scale, you're going to get your weight in pounds. We don't do English system in this class. So the first thing you're going to have to do after you get your weight in pounds is convert it. Now, I'm going to step you through a problem, and then you're going to get to do it. Let's say you step on the scale, and the scale says you weigh 100 pounds. Nice even number. All right? You're going to do the conversion 100 pounds times 1 kilogram divided by 2.2 pounds. So this will be 100 divided by 2.2. And you get that that is 45.45 kilograms. All right. So when you put this in your calculator, or you can do it by longhand, you get 45.45 kilograms. So you have your weight in pounds. You're going to need to write all this down. 100 pounds, or whatever your weight is. My mass in kilograms is M is 45.45 kilograms. The next thing I need to do is find the weight. The weight is Fg in newtons. So I'm going to take my mass in kilograms, which is 45.45 kilograms. I'm going to multiply that by gravity, which is 9.8 meters per second squared. And I find that if I weigh 100 pounds, that really is 445.45 newtons. So the first thing I want you to do is convert your weight from pounds to newtons. Now, draw a free body diagram. You're standing, and we're going to be pulling you with a spring scale. So Fg goes down, normal force goes up. One of your friends is going to be applying a force to you, and these aren't the greatest skateboards, so there's going to be friction in the back. Now, in this lab, we're not going to try to measure acceleration. We're going to assume that the sum of the forces in y is 0. In the first part of the lab, we're going to do it for static friction. And in the second part of the lab, we're going to use a constant velocity. So in both of our cases, our acceleration is 0. So you sum the forces in y. Sum of the forces in y is always 0 in these examples. So Fn minus Fg tells us that the normal force, which we need, is going to equal our weight. Solve it for n, Fn, and so my normal force is going to be 445.45 newtons. Now, I want you to stand on the skateboard and see how much force it's going to take to get you started. Let's pretend like you have a spring scale and it reads 50 newtons. So what that says is it takes 50 newtons of applied force to overcome the frictional force. Now your numbers are going to be very different. Now I want you to calculate the static friction. If it takes 50 newtons of applied force to overcome your frictional force, let's look what Newton's law says. The sum of the forces is going to equal 0, because my net force equation is for a case where there is no, we're not moving yet. So I have F applied going to the right. I have friction going to the left. That equals 0. So what this tells me is my frictional force has to equal my applied force. And you remember we read the applied force off of the scale, of the spring scale. So the frictional force that you have to overcome to get started is equal to that force that you read on your scale. So static friction is mu s Fn. I'm going to solve this for mu s. That's divide both sides by Fn. So that's my static friction divided by my normal force. So for this example, the static friction is that 50 newtons that I read on my spring scale, and my normal force is 445.45 newtons. And I get a coefficient of static friction of 0.11022. That's a reasonable measure of friction. Now, carefully, you're going to go into the hall and you're going to stand on the skateboard. You're going to get moving at a constant speed. When you're moving at a constant speed, neither speeding up nor slowing down, you're going to have a new speed, a new force measurement, and it should be less. Let's say it takes 20 newtons to keep you moving at a constant speed. You see, my force equations are going to be the same. My free body diagram is the exact same as it was, and because I'm moving at a constant velocity, my acceleration is 0. Because my acceleration is 0, I know that my applied force minus my frictional force has to equal 0. Therefore, my applied force is equal to my frictional force, or my frictional force is equal to my applied force. So the number you read off the scale is equal to your frictional force. Solve it. Fk is mu k Fn. So mu k is Fk divided by Fn. In this case, it's 20 divided by 445.45. And you get a coefficient of static friction in this hypothetical case of 0.04. Oh, we're just going to call this 5 because we got a lot of 9s after this. Now you can conduct the friction skateboard lab on your own.